Okay, 1.1, can change occur at an instant? So let's first talk about the fathers of calculus. We have Isaac Newton. And we have Gottfried Leibniz. Okay. So first, let's go ahead and try to answer the following question. Can change occur at an instant? So it says, Mr. Burst's distance from his house is modeled by the function d of t. While riding his bike to the store, he realized he dropped his wallet and turns around to find it. After finding his wallet, he finishes his ride to the store. So this is what this diagram off to the right is illustrating. So he's driving to the store, realizes he forgot his wallet, turns back around, grabs his wallet, and then continues on to the store. Okay, so it says, what is his average speed or rate of change for his trip to the store if he arrives after 8 minutes? So remember, rate of change is referring to slope. And we know that the slope formula is y2 minus y1 over x2 minus x1. So to put this in terms of our graph, since this is in terms of d of t, we're going to do d of 8 minus d of 0 over 8 minus 0. Because it says after 8 minutes, okay, meaning when he first starts his trip, the time is 0, okay? So then looking at the graph, we see that d of 8 is right here, so about 1,300 meters. So we have 1,300 meters minus, and then of course their starting value at 0 minutes is going to be 0 distance. Okay, all over 8 minus 0. And so we have 1,300 divided by 8, which is 162.5 meters per minute. Okay. So part B says, what was his average rate of change between 2 and 6 minutes? Okay, so average rate of change, again, is talking about the slope. So we're going to do the same process again. So we have d of 6 minus d of 2 over 6 minus 2. Okay, and since we're not given these exact values here, we're going to have to estimate just like we did before. So d of 2 is here, and then d of 6 is here. So let's say d of 6 is around a little below 900, so maybe 800. So we have 800 minus d of 2 is right here, so it's between 900 and 1,200, so let's say 1,000, all over 6 minus 2, which is 4. And of course, you can continue simplifying that and putting that in your calculator, but it just wants us to set it up. Okay, so again, part C says, what was his average rate of change between 2 and 3 minutes? Okay, so average rate of change, again, is slope. So between 2 and 3 minutes, this is d of 3 minus d of 2 over 3 minus 2. D of 3 is going to be right here. It's going to be very close to d of 2, maybe like 1,100. And then remember, we said d of 2 was 1,000 all over 1. Okay, so if we were to simplify this, this would be 100 meters per minute. 1,100 minus 1,000 divided by 1. Okay, now let's look at an instant. So it says, is it possible to know how fast he was going at an instant? It says, give an example of how to calculate a rate of change that would give us a close estimate to the instantaneous rate of change. So now we're no longer talking about slope. We're talking about instantaneous rate of change at t is equal to 2. So in order to do that, since we want to estimate at one certain point, we are going to have to try to find a value that is very, very close to 2. So find a value close to t equals 2. So this is going to be like t is equal to 2.001 or t is equal to 1.999. So those two values are very close to 2. Okay, now it says give a rough estimate of instantaneous rate of change at t is equal to 2. So there's two ways we could show this. One is we could use that slope formula, but plug in a value very, very close to 2. So this could be d of 2 minus d of 1.999 all over 2 minus 1.999. Okay. And then another thing we could do is we could draw a tangent line and then estimate the slope. So if we look up here, I would try to draw a tangent line like this. Okay. Then I would find 2 points on that line. So let's say like this point and try to estimate the slope. So that would be another way that we could do that. So let me just write that here. Draw tangent line and estimate the slope. So if you were to calculate it, it could be around 50 meters per minute. Okay, and again, that would be an estimate because we don't have those exact value points. So again, two ways of how we could estimate instantaneous rate of change. Okay, number 2 says B of T represents the buffalo population in the U.S. where T is measured in years since 1800. It says, what does B of 90 represent? Okay, so we're told that B of T is the buffalo population and T is years after 1800. So this is going to be the number of buffalo in 1890. Okay, 90 years after 1800. Okay, part B says, what does B of 50 minus B of 0 over 50 minus 0 represent? Okay, well, this right here is our slope formula. Okay, so this is going to be the average rate of change in buffalo from 1800 to 1850. Notice that anytime we were looking at slope, we said the words average rate of change. Okay, and then lastly, it says, what does B of 32 minus B of 31.999 over 32 minus 31.999 represent? Okay, so right here, since we have a number that is very close to 32, this is trying to represent instantaneous rate of change. So we would say this is an estimate of instantaneous change in buffalo in 1832. So it's trying to estimate 32, and 32 is representing the years after 1800. Okay, so just to summarize here, we had average rate of change, which we can abbreviate as AROC. Remember, we find that by a secant line, and we need at least 2 points to estimate. And then we have IROC, or instantaneous rate of change, which is approximated by using the tangent line, and we only need 1 point to estimate it. Okay, so just color coding it with the rest. Instantaneous rate of change, that's the green. That's finding a value very, very close to the instant and where it happened. And average rate of change, or AROC, is us finding the slope.